Hello and welcome to Math 1428 Alternative Delivery for the 10th of April 2020, and the topic we're covering today is section 5.1 in your textbook. And make sure you have pencil and paper ready. I hope you did a cursory pre-reading of the section so these examples will perhaps be ever more meaningful for you. Please also feel free to pause, rewind, and so on and so forth to test your understanding as we go through. And at the outset, I want to commend you for your endurance and persistence. We can make some magic today fighting against this crisis. You can stay the course, do the work. Teaching and learning still is possible. Grades will be earned and rendered, and your educational goals need not be deferred. I hope you're able to stay the course. Today's topic in chapter 5.1 is inverse functions. We have two primary objectives. The first one is to determine whether a function is what we will call and define to be one-to-one, and we'll have several characterizations of that. And if it is one-to-one, we can find a formula for its inverse. And we also can simplify expressions of the type f composed with f inverse of x and f inverse composed with f of x. So here we go with these. An inverse relation is defined in the following way. We have a set of ordered pairs. We can interchange the first and second coordinates of each ordered pair in a given relation, and that produces what is called the inverse relation. Similarly, we can talk about an inverse relation if it is defined by an equation. If a relation is defined by an equation, interchange the variables, that is, changing x for y and y for x, producing an equation of the inverse relation. Let's look at a couple of examples of this. The first one is shown here. You want to find the inverse of this relation. Hit pause, do the problem, and then we'll check and see how you did. Pause now. Let's see how you did. Well, you interchange the first and second coordinates, and this is the inverse, so it's the set of ordered pairs 8, 7, 8 minus 2, minus 4, 3, and minus 8, comma, 8. The next example that we're going to look at says to find an equation of the inverse relation. The problem 9 tells us we have x is equal to y squared minus 2x. Again, hit pause now, and we'll see how you did. Let's see how you did. So you interchange the x and y. So instead of having x equal y squared minus 2y, we have y is equal to x squared minus 2x. And this gives us a little bit of a hint as to what happens graphically with these inverse relations. Here, for example, is a relation, we're coloring it blue, and it's y is equal to x squared minus 5x. And you see what we have here. But then if we look at the inverse relation, which is this graph, we see that it is simply the reflection about the line y equal x, which is this dotted line. You're just reflecting it. That means if AB is on the function, if the ordered pair AB is on the function, then the ordered pair BA is on the inverse of the function. Now we'll move to defining one-to-one function. A function is called one-to-one if different inputs have different outputs. That is, if A is not the same as B, then f of A is not the same as f of B. Another way to say this is, or a function is one-to-one if when the outputs are the same, the inputs have to be the same. That is, if f of A equals f of B, then A must equal B. If it turns out that the inverse of a function is also a function, it is called, with this symbol, and this is called f inverse. That little minus 1 is not an exponent if this is a function. We just read it as f inverse. And so note that that minus 1 in f inverse is not an exponent. That means that f inverse does not mean 1 over f of x. It means something else. It means we're finding the inverse function, and we'll keep talking about that. Turns out that there's an intimate relationship that exists between one-to-one functions and inverse functions. If a function is one-to-one, then it does have an inverse that is a function. The domain of a one-to-one function ends up being the range of the inverse function. The range of a one-to-one function is the domain of the inverse. Here's a little diagram that may help you remember that, and that's very useful, by the way. And a function that is increasing over its entire domain is decreasing over its entire domain. If a function that is increasing over its entire domain, or if it is decreasing over its entire domain, it has to be a one-to-one function because it never doubles back and hits the same values again. Okay, let's look at a couple of problems that deal with this. We're going to do problem 17. The directions say, given the function f, prove that f is one-to-one using the definition of a one-to-one function. So number 17 is f of x is equal to 1/3 x minus 6. Hit pause now. Let's see how you did. So we have to show that if f of a is equal to f of b, then a is equal to b. So if I put a in, I get the expression on the left side of this equation. If I put b in, I get the expression that is on the right side of these equations. Now I can add 6 to both sides, and then I can multiply by 3, and I get that a equals b. So we showed that if we start with the assumption f of a equal f of b, then a equals b. That means that this function is one-to-one. Here's another problem. This is number 21. Given the function g, prove that g is not one-to-one. And so here we have g of x is equal to 1 minus x squared. So hit pause, do the problem, and let's go back and see how you did. Let's see how you did. Well, since g of minus 1 gives you the same value of g of 1, so we have g of minus 1 is equal to g of 1, but minus 1 does not equal to 1. That means it's not one-to-one. Both 1 and minus 1 are mapped to 0. If we have a graph, we can figure out if the graph is one-to-one by using a thing called the horizontal line test. You may recall that when we were determining if something was a function, we used a vertical line test. So this is our horizontal line test. If it is possible for a horizontal line to intersect the graph of f of a function more than once somewhere, then the function is not one-to-one, and its inverse is not going to be a function. Let's look at two problems here together. We're going to pause and do these both. Figure out if number 25 and number 27 are one-to-one functions. That is, do they pass the horizontal line test? Hit pause now, and let's see how you did. Well, the first one, every horizontal line is going to hit that function exactly once. It's hard to see down here, but you can look at the equation and see what is happening. It's getting closer and closer to 0. That's a horizontal asymptote. So the answer is, this passes the horizontal line test. Yes, this is a one-to-one function. Here, what we see is that many horizontal lines, for example, this one, y equal 3, will hit the function in more than one point. That means that is not a one-to-one function. We also want to know how to find the formula for the inverse. So, if f is a one-to-one function, that means it has an inverse. A formula for its inverse can generally be formed as follows. We replace f of x with y. Y is always f of x. Then, we switch x and y. And then we solve for y, and replace y with f inverse of x. So this will allow us to solve for these. Again, I don't do the examples in your book. Those are there for you to read through. You do different examples, and we do ones from your problem. So here are 3 problems I'm going to ask you to do. And there's parts A and B for each of these problems. We're going to look at 57, 62, and 63. For each one in part A, figure out if it's one-to-one. And if the function is one-to-one, you want to find a formula for its inverse. So you're going to do all 3 of these. So you're going to pause, give them a go, and then we'll come back and see how you did. 57, 62, and 63. Let's see how you did. Okay, so if we graph that, we see, oh, it passes the horizontal line test, and so we know it is 1 to 1. Now, what we're going to do is we're going to replace x with y. So instead of having y equals 2x minus 1, again, f of x is y, we switch the x's and y's. So everywhere where we have a y, we put an x, and everywhere we have an x, we put a y. And then we solve for y in terms of x. So y, we're going to add 1 and divide by 2. And so we get that y is equal to x plus 1 all over 2. And then we replace y with f inverse of x, and we find that f inverse of x is equal to x plus 1 over 2. Number 62, now this is something that we learned to graph in chapter 4. This has a horizontal asymptote at x equal to minus 1/2. And so it's graphed below, but you see, oh, it would pass the horizontal line test. Everywhere I could draw a horizontal line, it hits the function only once. So it passes the horizontal line test. It is 1 to 1. Now we're going to replace f of x with y. So we put y here is equal to this expression. Then we're going to, everywhere we have a y, we put an x, and everywhere we have an x, we put a y. Then we solve for y. Now, you might want to spend some time making sure that you can solve for y. These are problems that we've done before, but if we solve for y, we get y is equal to x plus 3 over 5 minus 2x. Make sure that you can do this step. And then last but not least, we replace y with f inverse of x, and we get this expression. The last one, this is y equals f of x equal x cubed minus 1. The graph is here, and we can say, does it pass the horizontal line test? And it does. So this is a 1-to-1 function. Then we're going to replace f of x with y. Then everywhere where there is a y, we're going to put an x, and everywhere there's an x, we're going to put a y. Then we're going to solve. Now the way we solve for y in terms of x is we will add 1, and then we'll take the cube root of both sides. So what we get is f inverse is equal to the cube root of x plus 1. We sort of alluded to this before, but now it's becoming clearer and clearer that the graph of f inverse is a reflection of the graph of f across the line y equals x. So if AB is on the function, then BA is on the inverse of the function. And so here's an opportunity for us to test that understanding. We're going to do problem number 79. So in each of these, we have the graph of a 1-to-1 function. You want to sketch the graph of the function, of the inverse. So in 79, we're going to use the fact that I know I have AB, 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 and AB on the function. We're going to realize it's symmetric with respect to this dotted line, and we're going to solve it. Hit pause now. Let's see how it did. Okay, so we reflect the graph of f across the line y equals x. The reflections of the label points are minus 6, minus 2, 1, minus 1, 2, comma 0, and 5.375. That's 5 3/8, and that's 1 1/2. And then we connect the dots in a way that has the reflection maintained. If a function is 1-to-1, then f inverse is the unique function such that each of the following holds. That is, if we start with x and we operate on that with f, and then we operate on that with f inverse, we get x back again for every x. Similarly, if we start with f inverse of x and then we do f of that, we get x. A lot of times when I lecture in class, I talk about in the morning, I like to be barefoot in my house, so think about that as being x. When I go to work at the College of DuPage, what I do is I put my socks on last, and then I put my shoes on, and then I lace my shoes up. When I come home, I do the inverse operations to get back barefoot. I unlace my shoes, take my shoes off, and then take my socks off. So that's an example of it's the inverse operations in the reverse order. Okay, so for the following function f, we're to use the composition of functions to show that f inverse is as given. Now this means if this is f of x, then this is f inverse of x. So we must show that if we do f of x and then we do f inverse of that, we get back x, and have to do the same thing when we do these in the other order. Hit pause now, and let's see how you do. Okay, so the first example, what we're doing is first we do f of x. And so f of x is this, but then f inverse says it's 5 times whatever the value was, minus 5 over 2. So now we simplify this. We distribute this, we get 2x plus 5, and then it is minus 5 over 2. The 5's cancel, so that is 2x over 2, and that's equal to x. If we do it the other order, what we have is that f inverse is going to be 5x minus 5 over 2. But then f is going to be 2/5 whatever we gave it plus 1. So if we multiply across here, what will happen is the 2's will cancel straight away, and we divide by 5. So what we get in this expression is x minus 1 plus 1 is equal to x. So you see both f inverse composed with f and f composed with f inverse of x both give us x. That means these are inverses one with another. The last kind of thing that can come up, this certainly comes up in trigonometric functions and other functions, is that sometimes the inverse of a function is not a function. The function is not one-to-one, but the domain of the function can be restricted to allow the inverse to be a function. This happens in your calculator when they talk about the inverse of certain trigonometric functions. So let's consider the function y equals f of x equal x squared minus 2. Now that's not one-to-one. Here's the picture, and you can see it does not pass the horizontal line test rather. But suppose we tried to find a formula for its inverse anyway, and we were to then replace f of x with y. That's what happens on this step. And then we interchange. Everywhere we have an x, we put a y, and everywhere we have a y, we put an x. And then we solve for y in terms of x. We get y squared is equal to x plus 2. But that means that y by the square root property is equal to plus or minus x plus 2. That's why it's not a function. But if I insist that the domain is x is bigger than 0, you see, if I were only talking about this part of the function, and that's the blue part down here, then it would be one-to-one, and I would have this being the inverse. And so you see, that would tell me that I would have to take the positive branch. So what happens is here, if I restrict it to being x greater than or equal to 0, then the inverse is going to be the square root of x plus 2. Now, more than ever, time is precious. Each day must count. Do the math, it'll make you strong. Reread this section, read the next section, and do some of the homework. And again, we always talk about every other odd. Now and always, take care.